Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 32, and this problem asks us to synthesize each of these compounds starting from benzene. So it's kind of a retrosynthetic analysis, so we have these three products and we need to form these, each of them from benzene ring. So let's start with the first one. So from benzene ring, we're adding one carbon and then we're oxidizing that one carbon to the highest oxidation level, which is a carboxylic acid. So we don't know how to add on a carboxylic acid directly yet. We can use a Grignard's reaction, but we haven't actually gone to that. And since this chapter is talking about reactions of aromatic compounds, we won't actually use Grignard's because I think that will be more steps than another approach that was introduced in this chapter. And that will be, for example, something like Friedel-Crafts alkylation and followed by oxidation of that carbon to yield our carboxylic acid. So what we need to do is first start from our benzene ring and count how many carbons we're adding. Well, we're only adding one carbon, so we will add that one carbon, attach it to a leaving group like chlorine, and add our Lewis acid to it for Friedel-Crafts alkylation, and then the product of this obviously would be your addition product, or actually this is a substitution product, being 1-methyl on any of these carbons on benzene because they're all equivalent. Now we've added all the carbons that we need to add. So the next thing is we need to oxidize this carbon, not just to an aldehyde, but fully oxidize it all the way to the carboxylic acid step. So what we need to do is we need to add some sort of oxidizing agent, and one of the examples that textbook uses is KMNO4, so potassium permanganate. This is a very strong oxidizing agent, and if you combine this with a little bit of heat, you can fully confirm that this is the carbon here, this exocyclic carbon or benzylic carbon is going to be fully oxidized to our carboxylic acid. And we know that these aromatic carbons won't be touched because of the stability of these carbons due to the fact that they are aromatic. So this is how we synthesize the first product. Now, what about the second product? So we've never actually learned how to add nitrogen or NH2 from using electrophilic aromatic substitution. We know how to do this from a benzene ring that has some sort of halide on it. For example, if it was a benzene with a chlorine or a bromine or a fluorine, we could do nucleophilic aromatic substitution because we know then that if you add, for example, sodium amide, then the amide would be a strong base, and you would have a elimination of your leaving group and then addition of your nucleophile being this NH2 minus. However, that first requires the generation of a benzene ring with some sort of halide attached to it. Something more easier that we could do is add a nitro group to it, which we already know how to do through electrophilic aromatic substitution, and then reduce that nitro to an NH2. So one way we could go about this is, and there are multiple ways that we can go about each of these. I'm just going through one, but another way would be to use this then NH2 as your nucleophile and the benzene ring as electrophile by making this reacting the benzene ring with, for example, Cl2 and FeCl3, and then you would make some sort of a benzene derivative with a halide, and then we could do elimination addition nucleophilic aromatic substitution to get this addition product. So actually I'll draw both ways just so we just see each way. So first I'll do the electrophilic aromatic substitution way, in which that we're going to first add our nitro group. So we know how to do that with HNO3 and H2SO4. And now we're going to add one nitro group on one of these carbons on the benzene. And then we got to reduce this nitro to an amine by adding hydrogen on palladium carbon. Hydrogen on palladium carbon. That will reduce only our nitro group and not the aromatic carbons to this amine group. But another way we could do this now is through nucleophilic aromatic substitution. And now we can make our benzene ring into the electrophile by reacting it with, for example, Br2Fe Br3. And then we get the addition of bromine. But now here's the issue. The issue on this is that we can have polyhalogenation product being formed. So now this would form a more messy product, and we would have to isolate this monosubstituted product here, and then in which then we could add, for example, sodium amide as a strong base in ammonia, and then we can get our product like this. So there's two ways to get to this example. I think the electrophilic aromatic substitution way is more clean, just because with this bromination step in the nucleophilic aromatic substitution method, you will get products that have polybromination. So you would have to isolate for this monosubstituted bromine derivative group to move forward with this reaction. The last example is that now we have addition of two groups. And whenever we have addition of two groups, it's always better to add the electron donating group first. So just like in the first example, we first added a carbon group to the molecule. And we know carbon group are electron donating, so they direct ortho and para. And this bromine group is in the ortho position. So that means that we would have isomers that are that can be directed to have this bromine exclusively at this ortho position. On top of the meta position, which we would have to isolate out of. So if we begin with that, with the benzene ring, you first want to add your carbon. So just like in problem A, we'll add that one carbon using Friedel-Crafts alkylation method. But now we won't oxidize it quite yet, because we want that directing effect of this CH3 for the ortho and para positions. So we can add the bromine, just like in this step here. But electron donating groups direct ortho and para, so we would get two products. We would get the ortho product, but then we would also get the para isomer. But then we would have to isolate for this ortho product to move forward, in which then we could oxidize this carbon to get the fully oxidized product, just like in A, which we use KMnO4, potassium permanganate, and a little bit of heat just to make sure that it fully oxidizes. And then we get this product of interest here.